Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the volumetric strain induced in a body due to applied forces. All of you know this linear strain induced when forces acts. So when forces acts on a body, its linear dimensions changes. So if it is acting in a x direction, the dimension in x direction will change. Simultaneously, it also induces strains in the lateral dimensions, that is y and z directions. So these dimensional changes will change the volume of the block. So that induces changes in the volume of the block. So this change in volume caused by the forces divided by initial volume is known as volumetric strain. So volumetric strain is the ratio of change in volume to the original volume or initial volume when it is subjected to loading. As a result of loading, the dimensions of the body changes, and this induces a change in volume, and the ratio of this change in volume to the initial volume is known as volumetric strain, and it is generally represented by EV. So EV is equal to change in volume divided by initial volume, or EV is equal to delta V by V. So the change in volume delta V you can find out as volumetric strain into volume. So if you know the volumetric strain, you can multiply with the volume of the body to find out the change in volume of the block. So volumetric strain has no unit because it's a ratio of change in volume to the initial volume. So both have the same unit, say mm cube and mm cube. So mm cube by mm cube, or centimeter cube by centimeter cube, or meter cube by meter cube. So that units will get cancelled. So volumetric strain has no unit. But change in volume delta V is strain into volume. So whatever unit you use for volume, so that will be the unit for delta V, that is change in volume. You substitute volume in mm cube, you will be getting delta V in mm cube. If V is in meter cube, you will get delta V in meter cube. Now let us consider a rectangular block. So we are finding out the volumetric strain of a rectangular block. The dimensions of the block, length L, breadth B and thickness T, and it is subjected to some kind of loading, and as a result of this loading, length will change, breadth will change, thickness will change. We have to find out the volumetric strain caused by this loading. Initial volume of the block is V is equal to LBT. Now let us take logarithm on either side. Log V, that's natural logarithm. Log V is equal to log of LBT. So volume is LBT, so that is the volume of the block is length into the cross sectional area, which is B into T. So cross section area is BT and length is L, so LBT will give the volume of the block. Now let us take logarithm on either side, that is natural logarithm. So log V is equal to log LBT. Now this log LBT you can split into three parts: log L plus log B plus log T. So log V is equal to log L plus log B plus log T. So if you go for partial differentiation, we will get del V by V is equal to del L by L plus del B by B plus del T by T. So you know del V by V is differential change in volume to the volume of the block, that is volumetric strain. So differential change in volume to the volume is volumetric strain. We can represent by EV. Del L by L is a differential change in length to the initial length, that is a strain in length. Del B by B is a differential change in breadth to the initial breadth, which is EB, strain in breadth, plus del T by T is a differential change in thickness to the initial thickness, it is strain in thickness. So volumetric strain you are getting as strain in length plus strain in breadth plus strain in thickness. So summation of strain in length, breadth and thickness, that is linear strain. Summation of the linear strain caused in length, breadth and thickness, if you add, we will get the volumetric strain of the block. Now to find out the volumetric strain of a cylinder, consider a cylinder having diameter d and length L, and its volume is area of cross section multiplied by length. Area of cross section is pi by 4 d square into length. So pi by 4 d square into length will give the volume. If you take logarithm on either side, you get log v is equal to log pi by 4 d square L. You can split that into 3 parts, log pi by 4 plus log d square plus log L, and it's equal to log pi by 4 plus 2 log d plus log L. Now if you go for partial differentiation, left hand side is log v. If you differentiate, del v by v is equal to 2 del d by d. So this log pi by 4 differentiation is 0, since it is a pi by 4 is a constant, so it is differentiation is 0. So left hand side log v if you differentiate del v by v. Right hand side this is 0, differentiation of this is 0. 2 del d by d plus del L by L. So we get, this is volumetric strain. Del v by v, differential change in volume to the initial volume, is volumetric strain. Del d by d is change in diameter, differential change in diameter to the initial diameter, it is diameter strain. So 2 times the diameter strain plus del L by L, differential change in length to initial length, is strain in length. So volumetric strain is 2 times diameter strain plus strain in length. So EV is equal to 2 times ED plus EL, or you can write it as EV as EL plus 2ED. I written the strain in length first plus 2 times strain in diameter. So volumetric strain of a cylindrical rod can be found out as strain in length plus 2 times the strain in diameter. Now let us consider a sphere having a diameter d. Its volume is pi by 6 d cube. Now if you take logarithm on either side, you get log v is equal to log pi by 6 d cube. So it is log v is equal to log pi by 6 plus log d cube. Log pi by 6 plus 3 log d. So you can write this as 3 log d. So log v is equal to log pi by 6 plus 3 log d. So if you go for partial differentiation, log v del v by v, differentiation will get del v by v, differentiation of this is 0, and this if you differentiate you get 3 del d by d. So del v by v is equal to 3 del d by d, or EV is equal to 3 times this, we know is a strain in diameter, so EV is 3 times strain in diameter. So volumetric strain is 3 times the strain in diameter. So this is the volumetric strain of a sphere. So rectangular block which you have considered, length L, breadth P and thickness T, its volumetric strain is EL plus EB plus ET. A cylindrical rod which is having length L and diameter T, its volumetric strain is EL plus 2ED. And for a sphere having diameter D, its volumetric strain is 3 times ED. So in general we can write the volumetric strain as summation of strain in x, y, z directions. So here x direction you have length, y direction you have thickness, so ET, plus z direction you have breadth, so it is, so EX is EL, EY is ET and EZ is EB, so it is EL plus EB plus ET. So in x, y, z directions, whatever x direction you have length, so EL, plus y direction you have thickness, so ET, plus z direction you have breadth, so EB, So adding all the three, you are getting strain in volume. So in case of a cylinder, so taking this as x direction you have length, y direction you have diameter, z direction you have diameter. Okay, so ex plus ey plus ez, if you take, in x direction you have length, y direction you have diameter, z direction you have diameter, so el plus ed or el plus 2ed. In case of a sphere, x direction, y direction and z direction, all directions you have diameter, so ex plus ey plus ez is 3 times ed. ed plus ed plus ed, you get 3 times ed. So volumetric strain is 3 times ed. So what you have to do is just sum up the strains in x, y, z directions. Okay, so it will be easy for you to remember this formula. So that's all for today. Thank you for watching.